Hello.
Yeah.
Today I'm presenting the radeco. I will speak about a bit about theory, and Sushant will speak about the implementation details and radeco structure. At first, yesterday there were a couple of talks about ECU, but I should remind you about intermediate languages. They are abstract representation to aid the analysis of computer progress, to simplify the higher, higher order analysis like decompilation, SMT solving, and so on. And they are heavily used for the academic research and real-world tools like ABAP, LLVM, and so on. And modern decompilation process is impossible without using intermediate representation or like hex arrays and WAP decompiler and so on. And there are other applications like SMT solving and automatic exploit generation and prevention and automatic patch generation. There are a lot of various intermediate languages. I wasn't listing them all, but in my previous talks, you can find them. The most common one. There are some limitations for those that already existed, like lack of the floating point support and lack of the SSE and AVX and other SMD extensions for the other architectures. And most of the intermediate representations or intermediate languages does not support a wide range of the architectures like radare do. And some of them are too big for the further SMT solving and effective decompilation because it will require a huge amount of process power to make a good mass model of them. And some of them are also problematically ported and running on the other platforms like Windows because, for example, BAP or BitBlaze are written in the kernel, which is hardly usable on the Windows platform. And there are other kind of limitations, for example, widely known and used almost in every new academic research tool about program analysis, LLVM here was created and designed for the compilation, not for the decompilation. So there are some parts of it are not highly usable for the decompilation and program analysis of binary code, and not invented here. ECU is a low level here of the radare and radeco chain. It is a string representation of the intermediate language and simply reverse Polish notation to improve the emulation speed and evaluation speed. At first, it is a set of the. It is a small set of instructions, and you need to specify the side effects for each instruction. So it will be useful for the emulation, but you need to make your analysis more complex. And it has, unlike many languages, which had two forms, binary form and string representation form. The ECU is string and binary form itself. So ECU-VM is just running the string representation of it. And there is a second, higher level intermediate language. It uses ECU as an input and it requires more metadata from the radare, like xx function names, types, and so on. Radeco, current implementation of decompiler, which contains the radeco il, using r2 pipe to talk to radare, and it's written in pure Rust. It was started like a Google Summer of Code project in the previous year, and it was initially written by two students, Sushant Dinesh, who is currently presenting with me, and David Creator. And it was completely done just in the summers, just in two summers. So it's quite an amazing result. Briefly, I will cover the stages of modern decompilers. At first, one of the most known one and one of the biggest stage, it's forming the SSA tree. It's a static single assignment form where each variable assigned only once. So usual equations transforms into the more equations where one variable can become a dozen of variables. I will use example later. And there are two different types of the SSA forming process. It's analysis of the memory-based access and analysis of the register-based access. So memory-based access is simply forming SSA variables from the reading from memory, like structures, like working with the pointers and so on. And register-based SSA can be sometimes tricky. For example, if you want to split small variables which are stored in the one register, like two 32-bit integers stored in the one 64 register, and sometimes even more tricky could be overlapping analysis of the overlapping memory regions, like unions or dynamic structs, or even the links, linked lists. Here we can see the control flow graph with a few operations, and on the left and on the right we can see the applied the SSA forming process. So each variable like mx, when you can see it's used 3 times in the different iterations of the node. So after performing some analysis, SSA form becomes the second x, which is a result of the first x minus 3, becomes a new variable. So it's easier now to understand how compiler works, because decompiling is a process, obviously reverse for the compiling, and SSA is one of the most important stages of the compilers. So we need to reverse this process. And there is another important concept of the SSA. It's a P function, which works with a conditional representation. Oh, sorry, wrong image. So The next stage, it's like a sub-stage of the SSA. SSA is a quite complex process, so it involves using a few sub processes, and there is a concept of the domination. It's a concept from the graph theory, and no, it simply means that no, the next node being dominated by previous node if every pass from the entry node or entry point start of the function of the program must go through the dominated node. And there are a couple of subsets of the domination. It's a strict domination if only one node dominates the next one, and they are not the same and not equal. And in immediate dominator is a node which is a unique node that strictly dominates previous next one, but does not strictly dominate any other that also dominates this next node. It's a quite not intuitive concept, but I should note it because it will be, because it will be mentioned in the radeco structure definition and description. There is also a dominance frontier, and it's simply better to show it on this graph, which is nodes starting from the first one. It's an entry point of the program, for example, and those nodes are operational nodes. And here you can see the dominator. It's a fifth node, sixth node, seventh node, and eighth node. You can see it's in the blue area. And why? Because those nodes are dominate nodes like 4 or 12, and domination frontier is marked as green nodes. It's 5, 5th, 4th, 11th, and 13th nodes. And finally, we need to know the dominator tree to figure out how we should correct variable names, which means simply like folding the tree, graph tree, to mark the same variables as one node. On this image, we can see a simple PFG graph, which was the same, which is the same as on the previous image. And here we can see the dominance tree. Obviously, first node is a starting node, and then we can see the nodes like second node, which is dominate the third node. The fourth node doesn't dominate any node, and so on and so on. It's easier to understand on the next example. Because, for example, this dominance tree is important for the code elimination and variables names. For example, we have for equations like a equal b plus c, b equal a minus d, c equal a minus d, and c equal c plus d. And here we can see that b is not used in these equations. It doesn't affect any result. So we simply can remove that node and shorten the list of equations, which becomes just a equal b plus c, d equal a minus d, and c equal b plus c. The second, it's not really important stage of the decompilation, but it can shorten the output. Is a constant propagation stage, also called as constant folding. We can see the some representation of the program written in the SSA form before eliminating the condition. And here we can simplify the form because we can see that I first is just constant value, and it's used in the later equation. So we can simply fold it into one and just write like j first equal 4. And the same, because this is j first plus 1 always will be more than 2, so we can eliminate the second part of the condition. And so phi function here also simplified, so it will become only one way to execute. There is also one more optional stage of the decompilation, but also removing a lot of code by shortening the equations. For example, like if we have a equation like register 1 is equal variable 1, register 2 like equal register 1 plus 1, and register 2 and variable 2 equal register 2. So we can simply output the variable 2 equal variable 1 plus 1. It's very useful for generating a highly readable C output. One of the most complex parts of the decompilation is value set analysis. There are various kinds of this stage, various algorithms, and in theory it can be optional, but also it's important to represent a good type system and good representation of the variables. Performs the tracking of every register and memory region access, and it collects date, integer, and float values via program like usually integer types are placed directly in the registers or in simple pointers, and it also collects values by reference, by pointers, like pointers to the structures or pointers to the integer and so on. And it's also can search the close fitted pointers to form structures. So if we will see the, if you will see that in assembly we can see an access to the stack by different offsets, we can in some cases suggests that it's just one struct or union. Value state analysis consists from the two important concepts. Usually, it's memory regions. It's as regions which are limited by the access patterns, like lowest addresses and highest addresses of the memory reading and memory writing. And A locations, it's finding for finding local and global variables. They are which are referenced directly and indirectly. Let's see. This is on an assembly example. Here we just pass the struct address and have an access to various fields and looping it. So it's an array of structures. It's a value set analysis will recognize and access at first as the structure fields, and the second is will recognize the looping over the array. Also, one of the stages is the types propagation stage. It collects all usages of equal variables, which probably will have the same type. And it's simplified version of the full-fledged type inference, and usually used in the simplest decompilers. And also it can be done in disassembly level, so you don't need to pass to convert everything to the SSA and perform value stage analysis, value set analysis, and dead code elimination. You can perform it on the raw assembly. But for radeco, it doesn't really need it because it's radeco will contain the full-fledged type inference. And for type inference, it consists of the multiple steps. At first, it assigns types to the terms, which means occurrence of the operation, and it separates functions and types into context. So each function has the context which will contain the future constraints. And it can load function prototype from external meta information, like, for example, function from the libraries, system functions, or maybe debug information. And finally, it will generate type constraints for every function and global context. And also, it can contain the standard types of platform, like, for example, Windows specific types, like a handle or bool, which is a double word usually. And it adds architecture specific constraints, like specific of the using of types on the specific architecture. For example, like a difference between of usage of C types on various platforms, like 32-bit platforms and 64-bit platforms. And finally, we will feed these constraints to the SMT solver, which will produce the model of the type system. How it works? For example, we have simple program which contains a linked list and a function which have an access to this list. Here we can see the disassembly of this function, and we can see how it's have an access to these variables. So type inference will find out the function an access to these variables by parsing an access by offset, and it will configure the types, which will at first the simplest type inference will recognize the handle, especially, for example, here we can see the close, which is a function with a known prototype, so we can add this in the constraint. I will not show you the full constraint system because it will not fit any size of slide. But you can find an examples of constraints in the papers I referenced in the end of the slides. And as I mentioned before, there are various sources of the helpful external meta information which can add more deterministic states for the SMT solver. It will need to be converted into the constraints. At first, it's external system calls and shared libraries for which you know the function prototypes and probably data types. Debug information, obviously, and signatory matching for finding function prototypes and argument types, which is useful to be done on the assembly level before feeding the information to the radeco. Also, obviously, it's marks of the reverse engineer at all stages. For example, like on the assembly stage, where human can change the type of the variable or mark the stack region as a type, and traces of EC emulation, or even the record of the full-fledged debug. All this can be added into the compilation engine in the form of the SMT constraints to simplify VSA and make the result more shorter. Usually, it's here I referenced a few papers which are useful to read if you want to understand the previously mentioned concepts much better, because I realize that it's hard to catch this all on the fly. And the next part of the talk will be a remote part. Sushant?
Yeah, I'm here, yeah.
So you are ready?
Yeah. Could we begin?
Yeah.
All right. Okay, so for the second part of the talk, I would like to answer two main questions. What is radeco? How is it organized? And if I want to contribute, what can I do and how is the code organized? So basically, it's split into two parts. One is about the design and the philosophy of radeco. And the second part is about contributing and how the code is organized and to ease into contributing to radeco. So the first question I would like to discuss is, why do we need another decompiler tool? There are so many decompilers out there. Some of them are open source. And why do we need another one? So the main problem with most open source decompilers is they don't take the interactiveness into account. They decompile the entire code and they do not allow the users to interact or fix mistakes or add their own analysis to it. This really limits its usability because decompilation is not really deterministic, as you're trying to infer properties from a low level and you're trying to add more information to it, which is unlike a compiler where you reduce information. So inferences can go wrong, and we have people and reverse engineers to be able to correct this mistake. The second reason is we want users to be able to add their own analysis easily by exposing APIs and write their own alternative implementations for their own needs. So keeping this in mind, the main design idea is to be minimalistic and have generics. Now, though these two might seem like conflicting ideas, the main problem for us is to optimize, to be able to make a trade-off between having generics and being minimalistic. So the way we do this is we make all the APIs generic and have a single implementation which works in most cases for these. Of course, if something better works better for your the use case of binary, you can always have another implementation, and we can do that. This brings us second part, support multiple implementations. Now, why do we need this? Every single algorithm or data structure we use has its own implicit advantages and disadvantages for a particular problem. So for different problems, it'd be nice to be able to have different implementations where it works the best. And the last part is being iterative and interactive. We run every analysis and every stage one after another and give users a chance to interact with the decompiler to fix the mistakes it makes or to improve the analysis and improve the final output that the decompiler produces. So keeping all this in mind, radeco can basically be broken down into three main boxes which are shown in the middle, each corresponding to one single aspect of the decompiler. The first one is the front end. The front end takes the source and converts it into the SSA form. So the source can be anything. It depends on where you're loading the SL from. It can be from radare tool, it can be from a file, or you could even write your own implementation to load SL from IDA or anything like that. And we use SLR, which is an external library used to parse SL strings and provide tokens. Now, SLR is kept a separate library because it can be used in many other applications other than just radeco. SLR does a few nice tricks which help making SL much more usable. For example, it keeps track of the internal variables that SLVM has in order to produce flag outputs. And whenever it encounters a flag, it also does a translation to equivalent instructions and gives it to you as a nice stream of instructions which you can then manipulate in your use case. Now, coming back to source, the source is just a Rust trait. So the question is, what is a trait? A trait basically represents a set of functions which are grouped together under a name. So these traits can be implemented on structures to give them capabilities of the trait. This is really useful by designing generics because then the functions can just say, I would like an argument of type T, where T is any type that implements a trait. So this is exactly what we've done in the front end. The front end accepts input from any type which implements source. So you can pass in radar to, you can pass in a file or any other structure which will give you the information. And a front end uses this information and algorithms to convert from raw SL into the SSA form. The algorithm we use to convert to SSA form is a modified version of the algorithm which is described in simple and efficient construction of static single assignment form. Now, we have to modify this because the original paper is designed for source analysis, so it assumes that it has hierarchical constructs like if, for loop, while loop, and stuff like that. So we have to make minor changes to be able to adopt that to the binary level. Now, I'll take a short detour and talk about the radeco IR itself, because this will be useful while discussing the analysis. So radeco IR can basically be broken down into two components. It's a graph-based IR, which has a control flow graph, and it is superimposed with the expression tree on top of that. So here is a control flow graph. You can see that it has an entry node and exit node, and there are three nodes that are actually just part of the main graph. The entry and exit are not actually part of the function. So the entry node provides definitions to register flags and memories, which is used by the expressions later on in each one of the individual blocks. And exit provides a sync to write these registers, flags, and memories so that all the operations or all the modifications in the particular functions are recorded. So if you zoom into one of these nodes, this is how a typical node would look like. So you have a block node which has the address of the block, and then we have expression nodes. The list of valid operations are mentioned in the list on the right side. And if you observe closely, there is no conditional operation, like there is no conditional jump or stuff like that. So how do we handle this? The block basically has an edge called a selector, which points to the node which decides the control flow. So here in this example, you can see that the selector edge points to the comparison operator creator, which takes in two expressions, sub-expressions which are just subtrees. So depending on whether the OP creator evaluates a true or false, it takes the true or false edge. The block takes the true or false edge. Now, radeco IR supports coarse-grained memory SSA, meaning that any modification to the memory generates a new instance of memory. It does not keep track of where the memory write is. So memory is treated as immutable. So every store operation you perform is going to generate a new instance of memory, which is later going to be used for loads and stores. So in this example, as you can see, the OP store takes memory as the first operand, and location and write as two expressions. And in the subsequent load, takes the memory output from the store as its first argument, and location to load from the second argument. Now, the disadvantage to this approach is, anytime you modify memory, regardless of what address it is, you're going to create a new instance of memory. So you need to keep track of what you've stored at what location if you want to perform a more detailed analysis. But it's a nice way to do things in a very simple way without tracking each location, making each location an individual item. Now, the IR has a graph-based representation, and you can also see a graph output. This is output by radeco, but this gets very hard to debug because of the thousands and thousands of nodes. So to simplify, we also have a text-based IR. So text-based IR is inspired from LLVM's IR and shares many common similarities with it. The first thing to notice is that functions are defined using the define func primitive, and it takes the identifier, which is the name of the function, and the argument list, followed by an arrow mark with return type. Now, in this case, the function arguments and the return type are unknown because the IR has not been passed to type instance phase yet. But we already have support, some support for this in place. Blocks are labeled as BB underscore and the address of the block. Of course, labels can have any custom name depending on what analysis was performed earlier or information from radare 2. But by default, they're labeled as block followed by the address. Now, since the IR in SSA form, we cannot assign variable which has already been assigned before. We should have a single definition. So temporaries are used for this, and all temporaries begin with the % sign and is followed by a number in serial order. And it is never reassigned. So when you see a number, you know where it's going to be defined. Constants begin with a hash and is followed by X, which represents hex, D for decimal, O for octal, or B for binary. So in this example, hash x8 is equal to OX8 in hex. All data types begin with a $sign and is followed by data type and the width of the data type. So in this case, you can see temporary 1 is unknown data type again because we have not run the type inference and is of size 64. So how do we know that 64? Well, the subtraction operation takes RSP as one of its operands, which is of type 64, and this seems to be a function prolog, so it's probably an assignment to RDP, which is of type 64, and so radeco identified that and it's labeled as 64, so it's put as 64. Okay, so as I spoke about earlier, store creates a new memory operand, which is shown here. So store takes the previous memory operand, that's $5, which is written on the store, and then %6, which is the memory location, and writes off 0 to it, and generates a new memory %7, which is subsequently used in load. Jump expressions are of the form, condition jump expressions are of the form jump if condition, followed by the true target, else false target. If the false target is the next instruction, then this part is omitted because it makes it commit to it. Now, why do we do this? Yeah, once we encounter a call, we cannot say what register or memory the callee function is going to modify. So the safest assumption is that the callee modifies every single register and writes out memory. So because of this, we pass in every single register and memory as an argument. But this is hard for analysis because we essentially lost all the information that we tracked until the call statement. So this is fixing one of the phases, and I'll be explaining this when we come to the slide about analysis. Okay, so now we go back to the boxes. The second box is the analysis. So the analysis takes the SSI input from the front end, optimizes it, adds inferences, enriches the information, and then passes it on to the next phase. So the analysis in radeco are all completely optional, and you can choose what analysis to run on what binary. And it's up to the user or the radeco pass manager to select these passes. You can also add your own passes out of the tree because that is one of the main design ideas here to make it easy to write your own analysis passes. And the list of analysis is ever growing, and with each analysis, we have to improve the final decompiled output. And as I mentioned earlier, each analysis is iterative, meaning you have a chance to interact with the decompiler after each pass of the analysis. So the first analysis is constant propagation, which is labeled as SCCP, which stands for which stands for sparse conditional constant propagation. So it simultaneously removes dead code and propagates constants. Traditionally, you have a constant propagation phase, which is followed by dead code elimination, and then you alternate between these two to achieve the best output. But SSCP combines these two into a single phase to perform a better job at propagating constants. The second one is dominator tree. Now, these have many applications. One of them is using constant sub-expression elimination. The other one is to identify loop headers and loop bodies during decompilation. So that is really important phase. And then common sub-expression elimination eliminates sub-expressions which are evaluated continuously. For example, if you have a memory access to RBP minus 8, each time the binary is going to access memory, it's going to recompute this address. So you're going to see that in IR over and over again. Now, what common sub-expression elimination does is it stores this in a temporary, and then the temporary is directly reused instead of having operations to recompute this every single time. The next one is subgraph matching, which is also called grep and replace. It's basically used to reduce common machine idioms to simpler forms. A common idiom in x86 is, for example, XOR EX, which is used to set EX to 0. And having this in the decompiled output would be confusing. So depending on the architecture, you can have grep and replace patterns to replace machine idioms to their simpler forms. The next one is interprocedural analysis. Now, more than analysis, this is a framework which can be used with any of the other analysis. It is used to propagate information across function calls to improve the analysis. For example, currently we are using this for call summary information. In the call summary information, we travel the call graph of a binary recursively, and we summarize the effects of that call. Now, what does the summary contain? It contains information of what registers remain a constant after the call, what registers are modified for the call, and what memory is written out by the call. So once we have this information, it would be very easy to fix up the IR which we saw earlier to only pass in the arguments, registers as arguments which the function modifies, and also only write out the registers which the function modifies and keep everything else constant. The last two are value set analysis and type inference. These two are work in progress and not complete yet, but most of the frameworks are already there. So value set analysis is useful to be is useful in type inference phase, and it's also useful in finding targets for indirect calls. So whenever we have an indirect call, you will not know where the jump goes. as it was mentioned earlier, we generate type constraints and we solve the constraints to get the type. I'm going to go in a bit more detail into that. So whenever we have a known function call from a standard library, we know the type of arguments it takes. Now this information is loaded in from radare, and we propagate this information in the tree that we saw earlier. And with every use of a variable, we set constraints on it. For example, if we have an addition operation between an integer of size 16 and integer of size 32, then we generate a constraint which says this particular variable has been used in addition of 16 and 32, so we need to narrow the type down to one of them. And these constraints are later translated to upper and lower bounds, which help us in determining the equivalency type finally. The last phase is the backend, which takes in the optimized SSA and all the inference from analysis and produces some usable result. Now for a decompiler, the result would be pseudo-C output, but of course it's a generic binary analysis framework, so it could be used for any purpose that the user wants. For example, you could use the optimized SSA to generate a recompiled binary to some other architecture. You could use it for symbolic emulation or symbolic execution, or you could use it for plain emulation purposes. Now, the backend is also implemented as a trait. So you could have a C writer, you could also write another implementation which gives you Python output and everything like that. The C output itself has two phases within it. The first one being converting SSA to a basic C AST which supports basic C constructs like addition, subtraction, and only one kind of loop, the while loop, and there's no increment or decrement. And the second phase would be to make this output prettier, and so it's passed through a sugaring phase where you convert the while loop into a nice for loop, and you name variables more nicely based on how they're used and things like that. So again, we can see that it gives you a chance to interact with the decompiler and directly influence the output that you see finally. Okay, so anyone who's following along now would be interested to know how is the code organized. I want to contribute to it. So this section deals with that. So the code organization is similar to the three blocks which we spoke about earlier, with addition to middle and utils. The front end contains four files which are important, and the SSA constructor is the one which takes in the source and converts it into the radeco SSA IR, and source contains the trait source. So if you're ever curious as to how do I implement a new source or to integrate radeco into my project, source is where you need to be looking for it. Now, bindings and containers can go hand in hand. Containers organizes instruction which you load from radare2 into modules and functions. A module is basically an entire binary which is loaded. Now, you can always load in multiple binaries because binaries have dependencies like libc. So each of those can be loaded to separate modules, and each module contains several functions in it which are analyzed one by one. Bindings is basically structures and definitions to be able to declare and manipulate variables. Bindings are important because types and function arguments, that is both formal and actual arguments, are expressed in terms of bindings. And bindings can also be named, so it can be easy to refer to variables based on bindings. It also tracks the usage of each variables and helps us propagate the information that we obtain from one place to another. Now the second folder is middle, which is supposed to be called libir, but it's called middle for historical reasons. This contains all the code which is required for our IR. So the SSA folder contains the definitions to manipulate and build the SSA form. So everything that is related to SSA, adding a node, deleting a node, adding edges, getting users, everything is going to be knowledge if you want to use radeco IR by itself. It also contains several helper methods for debugging and viewing output. The main two are dot and IR writer. Dot converts the internal SSA to a graph which is viewable, and IR writer writes out to the LLVM like IR output which is all earlier. File placement and reg file are used during the SSA construction phase. Reg file passes the SSA definitions which is provided by radare2 into an internal representation, and also determines tasks when you access the soft register. For example, in x86 you have EAX, but you can also access it as AX. So the reg file makes these translations by adding bit shifts and masks when it's needed. The analysis is each analysis is present in a self-contained folder inside the analysis, and these are exactly what we spoke about earlier, with each analysis having a folder by itself. So how can you contribute? To begin with, we have beginner issues which are marked on the bug tracker. Me or xvilka will help you out with these. And these are basically there to get you acquainted with the code base and help you understand. We know Rust is a new language and it can be a bit intimidating to get started of it, but it's completely worth it and it's very easy to do it. So we have beginner issues to get you started with it. You could also write tests. Most code have tests, but they're kind of inadequate for the number of cases which we can run into when we're analyzing a binary. So it'd be nice to have more tests. If writing code is not something you have the time for, you can also help us with documentation. Major part of radeco has documentation, but it's very minimalistic, and it'd be nice to expand on these. And the last two are bug reports and feedback, which are very essential for us to drive the project forward. It's very hard for us to test all our analysis against each binary out there, so it would be good if people could test it out on different architectures, different binaries, and come up with a report. We also have a tool called Minitech as a part of the radeco lib repository, which explains on how you can run radeco, print and run radeco easily and report errors to us and all that stuff. And feedback is important for us to decide what features we should work on next, what users are looking for from the decompiler, and also identify the weak spots. So moving forward, what am I planning to do as a part of this project? Plan to have regular release cycles and coordinate it with the R2 release cycles, and implement a major feature in every single one of those. So for the upcoming cycle, I plan to have full type inference and pseudo-C output available. They're mostly there except for the connecting pieces which link them to the other parts. So it shouldn't be too hard to get that up and running. And the next one is to get the radeco tool up and running against a later version of radeco lib, because that is what helps us finally get the feedback from the users. And radeco lib is interactive, so you need to be able to test out whether it's actually working all the way we want it to be. Okay, with that I end my talk, and if you have any questions, I'll be able to answer them.
So, questions? Okay, I want to add a couple of words, especially about radeco. As Sushant mentioned before, there is a mini decompiler, but it's a command line. So we have a higher level order radeco tool, and what he means by more interactivity. In the ideal case, it would be nice to have something like radare interface, for example, so we can be able to change information on the every stage of the decompiling, from the constant propagation to the dead code elimination. For example, we can keep some code from the cutting by the algorithm or rearranging the stage. So, for example, we can run some stage twice after performing some analysis. For example, constant propagation and value set analysis, rerun them after the type inference, so it can give you a different result. Because the compilation is a quite complex task, So it can be fully automatic. It requires also an input from the reverse engineer, and it's very important. It's like a difference between the string disassemblers and interactive disassemblers. Same applies to the decompiler and in an even broader range. Okay, thank you.